More often, we're going to want to look at a function and determine all of the points of discontinuity, or rather, figure out where is it continuous and where is it not continuous, rather than investigating a single point. So we're going to look at a few examples of that here. But before we do that, we're going to give a theorem here that will make our examples a lot easier. Our theorem here first says a polynomial function is continuous for all x, and this is a really, really nice theorem. So if you come across a polynomial, you essentially know it's not going to give you any problems. It's going to be continuous everywhere. You're not going to have any weird spots where something odd is happening. We like to work with polynomials. Those are kind of the nicest, the easiest cases to work with. The other case here is if we have a rational function. So here's just the definition of a rational function. I always say a rational function is just a function that kind of looks like a fraction. This is continuous for all x for which q of x is not equal to 0. So q of x is just the denominator. So it's continuous everywhere except for x values that make the denominator 0. So if I have a rational function, I'm mostly just interested in where is the denominator equal to 0, because I know, again, based on our previous work, that will either be the location of a whole or a vertical asymptote. And we can go and find out which exactly it is, but if all I'm interested in is where is this function continuous, then I just need to look at the zeros of the denominator. So here in example 3, I have this rational function. I want to determine where this function is continuous. So I'm going to look at this. Again, this is a rational function, so I'm mostly interested in where is that denominator equal to 0. So I'm just going to take that denominator, x squared minus 1, and set it equal to 0. I don't care so much about my numerator. Now if it asks, hey, what type of discontinuity do we have, then we might be concerned about what the numerator looks like, because that would tell us whether we have a whole or a vertical asymptote. But here, all I'm looking for is where is this function continuous. So I don't really care what type of discontinuity it is. And then I'm just going to solve this equation. Take my denominator, set it equal to 0, solve this equation. You can do that however you'd like. Here you could use square roots. You could factor. I'm always partial to factoring, so I'm going to factor this here. I know this is a difference of 2 squares, x plus 1 times x minus 1. Set it equal to 0. And take each factor, set it equal to 0. X plus 1 equals 0. X minus 1 equal to 0. Gives me x equals negative 1. And x equals positive 1. So it's continuous everywhere except for these two values. And how I would like you to give your answer is interval notation. So you could say, well, it's continuous for all x values except for negative 1 and positive 1. But we're going to be using interval notation a lot in this class, and I want you to be comfortable using it here. So if you haven't seen interval notation, you might want to start by just making a little number line right here. So negative 1, positive 1. I'm going to put those two x values on my number line. And essentially what I'm saying is that my function is continuous everywhere except for this value, negative 1, and this value right here. So I've essentially broken my number line up into 3 chunks. I have this part right here. I've got to the left of negative 1. I've got between negative 1 and positive 1. And then I've got to the right of positive 1 over here. So when we talk about interval notation, we have 3 separate intervals to talk about here. Actually, let's do those we'll do those in blue. So for our first interval right here, we need a left bound, comma, a right bound. So here, this just extends infinitely to the left forever, so we would say our left bound is negative infinity, and our right bound is negative 1. It stops being continuous at negative 1. Neither one of these points is included, right? Negative infinity, first of all, not a real number. We can't contain that in an interval, so we're going to use parentheses around that. As well as negative 1, we said, hey, our function is not continuous at negative 1, so we're going to put parentheses around that as well. Next up, I think this is probably the easiest interval to write here. I just want to talk about the area, the spot between negative 1 and positive 1. So here I would have negative 1 to positive 1. And again, neither one of those points are included. We said those are discontinuities. The right-hand side to the right of 1 here, starting at 1, working my way infinitely to the right to positive infinity. Again, neither one of those points are included. We are using parentheses. Later on in this section, we will talk about instances in which we'll be using brackets here. So if I wanted to give this in interval notation, I would say negative infinity to negative 1, negative 1 to positive 1, 1 to infinity, something like this. You might see commas in between these, and if you use commas, that's fine. You might also see, sometimes I'm guilty of this, I'll use something from set notation, which is way later on in math, but I might put a little U for union right there. To be honest, I don't care which one you use. I'm not going to take points off for using one or the other. I believe our textbook just uses commas, so I think I'm going to try and be consistent with that. But as long as you have these 3 intervals listed, that's going to be what I'm checking for. That's what I'm interested in seeing. It's continuous on these 3 intervals. In part B, I have another rational function. I have 3x squared minus 6x plus 7 all over x squared plus x plus 1. So I'm here trying to solve this equation, x squared plus x plus 1 equals 0. And I look at this guy and, well, doesn't look like it factors particularly nicely. 2 numbers that multiply to be positive 1, add to be negative 1. I can't think of any off the top of my head. So what I would do in this case, generally if something does not factor, it looks a little bit uglier, I'm going to use our good old friend, the quadratic formula, which if you don't remember, that's okay. Remember, it says x equals opposite of b plus minus square root of b squared minus 4ac all over 2a. So I'm just going to use this to solve this particular equation. In this case, it's rather nice because a, b, and c, right, this is 1x squared plus 1x plus 1. So a, b, and c are all 1 here. So x equals opposite b, so opposite 1 plus minus square root b squared. This is going to be 1 squared minus 4 times a is 1 times c is 1. Divided by 2a, that's 2 times 1. So here in this case, let's see, negative 1 plus minus square root 1 squared is 1, minus 4 times 1 is 4, all over 2. Let's finish up over here. Negative 1 plus minus square root 1 minus 4 is negative 3 over 2. And hopefully at this point you stop right here and this jumps out at you, say square root of negative 3. I know that square root of a negative number, that is not a real number. Here we have a complex number. So what does that mean for us? That means that this equation right here that we started with, this guy, has no real solutions. Again, we're just sticking to the real numbers here in Calculus 1. We don't care so much about imaginary or complex numbers. So we're sticking to real numbers, and we just said there's no real solutions. We could find the imaginary solutions if we wanted to, but they don't really have any big implications for us. So if, in this case, there are no real solutions, what that means for me then, if I have no real solutions, that means it's continuous everywhere. So this function is continuous everywhere. And again, I'd like to give answers in interval notation. So if it's continuous everywhere, we're going to say, well, it's continuous on negative infinity to positive infinity. Here is my solution.